G'day everybody, this is part 2, this lesson where we explore some fundamental concepts with probability. Last lesson we looked at how we make Carnot maps, probability tables. We also talked about conditional probability. In this lesson we're going to cover the way we use tree diagrams to organise information, which is very useful for some problems. We'll use those probability trees to calculate probabilities, including another conditional probability, and near the end of the lesson we'll have a discussion about what it means for two events to be mutually exclusive, and also what it means for two events to be independent of each other. You might want to pause the video and read this question. We're going to use this question as an example of using a probability tree diagram to answer two questions. Essentially, we've got student Jane who completes maths exams in the morning. If this is the case, there's a 90% probability that she'll pass. The same exam in the afternoon, there would be an 80% probability that she will pass. And we're also told that 60% of her class time is in the morning. And we're going to look at two questions. What's the probability that she'll fail her next exam? And this is given that she doesn't yet know whether it will be in the morning or the afternoon. And we're also going to look at the question, if she passed her last exam, what is the probability that she completed it in the afternoon? So if you need a bit more time to absorb that information, please pause the video. Let's look at how we will construct a tree diagram. The first stage of this problem concerns whether it's going to be the morning or the afternoon. We're told that 60% of her class time is in the morning, and you'll notice that I'm not using A to represent afternoon. I'm using the complement of the morning. So another way of thinking about the afternoon is to use the complement of M. In the next stage of the tree diagram, we'll explore the probability that she'll pass or not pass. So in the morning she could pass or not pass. In the afternoon she could pass or not pass. Not pass, of course, meaning failing. What we'll see at the bottom of the tree diagram are all the different intersections of these two events that we could have. So it could be a situation where it's the morning and she passes, the intersection the morning and she fails, the afternoon and she passes, the afternoon and she fails. That covers all of the intersections for these two events. Two events being whether it's morning or not, and whether she's passing or failing. So at this stage I've taken the information that I've got given in the question, and we can see that we're using those probabilities on each of the branches of the tree. So 60% of the class time is in the morning. If that's the case, 90% of the time she will pass that exam. If it's the afternoon, then 80% of the time she will pass that exam. So let's look at how we complete the rest of the diagram. So you can see here I'm using the complements of those probabilities. 60%, 40% of the time must be the afternoon. If she passes 90% of the time, the complement is that she'll fail 10% of the time. This is in the morning. The complement of 80% is 20%. So probability trees are built up of complementary probabilities. And here I've added all of the intersections, and we do this by multiplying our way down the tree. So 60% of 90%, or 0.6 times 0.9, is 0.54. So that is to say, if 60% of the time is in the morning, and she's going to pass 90% of that 60%, then 90% of 60% is 54%. Or 0.54. The rest of the 60% must be the 6%, and we'll see those two add to give the 60% of the time in the morning. So they are also, well, not exactly complementary, but they go together to make that 60%. Looking at the other branches, we can see that 32% of the time she passes in the afternoon, and 80% of the time, 0.4 times 0.2 equals 0.08, she fails in the afternoon. And so that completes the probability tree. So from this diagram, we're going to use the information that we've analysed here and answer those two questions. First of all, what's the probability that she will fail her next exam? Not knowing whether it's going to be in the morning or the afternoon. There's two cases, two intersections where she will fail. So the probability that she will fail, you can see the way I'm using the notation here, will be the sum of two probabilities. There will be a probability that she'll fail in the morning. There will also be a probability that she'll fail in the afternoon. And so adding those two parts of the diagram together, failing in the morning, failing in the afternoon. So that's 0.06 plus 0.08, which is 0.14. So there's a 14% chance that she will fail the next exam, not knowing whether it's the morning or the afternoon. The second question, this is the conditional probability. If she passed her last exam, that's the condition. What is the probability that it was completed in the afternoon? So I've set up here the conditional probability formula. So the probability that it was the afternoon, given that she passed. And using the formula that we covered in the first part of this lesson, or the last video, it will be the probability of the intersection of those two events, that it was the afternoon and she passed, divided by the probability that she passed, not knowing whether it was the afternoon or the morning. That intersection at the top, there's two ways that she can pass. This is the bottom, this is the denominator. What's the probability that she will pass? 54% of the time it will be in the morning, and 32% of the time it will be in the afternoon. So that will be those two percentages together will give us the probability that she passes. And we can see the intersection right here at 0.32. So putting those in and calculating that probability, we can see we're going to have 0.32 divided by 0.86, which we can convert to a simple fraction, or we might approximate it with a percentage. It would be roughly 37.2%. So if she passed her last exam, the probability that she completed it in the afternoon is roughly 37.2%. So there we've used a tree diagram to answer two questions. And importantly, it's another way of looking at information that is given in a problem and organising it in a way that we can understand the various combinations of those events. We're going to have a discussion about mutually exclusive events. There's basically two definitions that are directly related to each other. You can see here I've got a picture of a pizza. It's been divided into 8 equal sections. Some of those pieces include mushroom, some of the pieces include pepperoni. We can see that there is no overlap of pepperoni and mushroom. So the probability of getting pepperoni, given that you've got mushroom on one of your random pieces, is going to be 0. And we can see that must mean that the intersection is equal to 0. If this is our conditional probability, it's equal to 0, then our numerator must be 0, and we can see that the probability of A intersection B is equal to 0 for mutually exclusive events. And that's sort of reflected in the way the pizza is constructed. We can see that there's no intersection of pizza and mushroom. If we compare that to this different pizza, we can see that there is an overlap. In this particular pizza, we can see that the probability of getting pepperoni, given that you've got mushroom, is going to be a half. So we can see there are 4 pieces with mushroom. If we get one of those pieces at random, the probability that we'll have pepperoni is a half. Importantly, it's not equal to 0. And also we can see that the probability of getting pepperoni and mushroom out of the whole pizza is 2 out of 6, or 1/3. And again, that intersection is not equal to 0. So here we're looking at 2 events: the event of getting mushroom on your randomly selected piece, the event of getting pepperoni. In this case, they are not mutually exclusive, because neither of those probabilities are equal to 0. And if one is equal to 0, the other one has to be equal to 0 as well. So just by way of summarising mutually exclusive events, generally this is the way we interpret the definition. If the probability of the intersection is equal to 0, then we would say A and B are mutually exclusive. Down here we can see the addition rule, which is a general case for any 2 events. So if this part of the rule is equal to 0, it leaves us with a simplified addition rule. So in the case of mutually exclusive events, the probability of the intersection of the union of A and B is the probability of A plus the probability of B. Let's have a look at independent events, which is a different concept. I'm showing you a pizza where the probability of getting pepperoni is clearly 1/2. If we ask ourselves, what's the probability of getting pepperoni given that our randomly selected piece has mushroom, what would that be? So here we're looking at the same pizza, but I've sort of shaded out the pieces that don't have mushroom. So given that we're going to get one of these 4 pieces at random, what's the probability that we'll end up with some pepperoni? Again, now 2 out of 4. Over here it's 3 out of 6, which is 1/2. Here it's 2 out of 4, which is also 1/2. So the condition that we have mushroom on our piece of pizza did not affect the probability that we're going to end up with pepperoni. And so in this case, we would say the events of getting pepperoni and getting mushroom are independent of each other. The presence of one condition doesn't affect the probability of the other. So by definition, events A and B are independent if the probability of A is equal to the probability of A given B. So given that B has occurred, the probability of A is unaffected. Generally, for any 2 events, the conditional probability is our formula here. So if we're saying that the probability of A is equal to the probability of A given B, and we use that to replace the probability of A given B in this formula, that formula then rearranges to be the probability of the intersection of A and B being the product of the probability of A and the probability of B. So that's an equation that is true if and only if the events are independent. And so being able to show that equation is true is also a way of being able to verify that 2 events are actually independent. So just to be clear, to demonstrate whether events A and B are independent, you can either show that the probability of A is equal to the probability of A given B, or you can show that the probability of the intersection is the probability of A times the probability of B. So these are the things that we aim to do in this lesson. We've talked about tree diagrams, mutually exclusive events and independent events.